Ever stop to think what's actually happening inside your phone? I mean, it seems super complex, right? Well, today we're going to pull back the curtain on this one simple but really powerful secret that runs it all.
Just take a look at this. It's a circuit board. Looks like a tiny futuristic city, doesn't it? A maze of shiny lines and little components all humming with electricity. And you know what? Every single gadget we own, from the phone you might be watching this on to massive supercomputers, is built on something just like this.
But here's the crazy part. There are no moving parts, nothing. So how does it think? How does this completely still, silent thing make millions of decisions every single second? That's the real mystery we're going to unpack.
Okay, let's get into it. To understand how all this magic works, we've got to peel back the very first layer. And I mean the most basic, fundamental idea there is.
And here it is, the big secret. Everything, and I mean everything, from the most complex calculation to the silliest cat video, gets broken down into one simple choice. Is a switch on or is it off? That's it. We call on 1 and off 0, and believe it or not, that's the entire language computers speak.
So you might be thinking, how on earth do you build our entire digital world with just two symbols, a 1 and a 0? Well, for that you need a set of rules, a special kind of math that tells these ones and zeros what to do.
And that's where something called Boolean algebra comes into the picture. It's basically the mathematics of logic. It's designed to work with just two states, true or false, 1 or 0. And it gives us these powerful tools called operators. You've probably heard of them. And, or, and not. Think of them as the grammar, the verbs of this digital language. They're what let us combine the ones and zeros to actually make decisions.
Okay, so this math is great in theory, but how do you get a tiny piece of silicon to actually do it? How do you take these ideas and make them, well, real?
The answer is something called a logic gate. You can think of them as microscopic little switches. Seriously, these are the tiny, fundamental building blocks of every digital circuit. And each little gate has just one job, to perform one of those simple Boolean operations we just talked about.
All right, let's meet the first one. This is the AND gate. And what you're seeing is its truth table. It's just a simple chart showing what it does. Look closely. The output is 1, or true, only when input A and input B are both 1. If even one of them is a 0, the output is 0. So yeah, it's a pretty strict gate.
Here's a simple way to think about it. To go on that Goa trip, you need your parents' permission and you need the money, right? Both have to be a yes. If one is a no, the trip is off. That's exactly how the AND gate works.
Next, we have the OR gate. Now this one's a lot more chilled out. The output is a 1 if input A is a 1, or if input B is a 1, or even if both are 1. As long as at least one input is a yes, the output is a yes.
And finally, the simplest gate of all, the NOT gate. People also call it an inverter. Its job is, well, exactly what it sounds like. It takes one input and just flips it. So a 1 becomes a 0 and a 0 becomes a 1. Dead simple.
So there you have it. And, or, and not are three basic building blocks. On their own, they're pretty simple, right? But this is where the real magic begins, when we start linking them together.
When we connect them, we create something called a combinational circuit. And the most important thing to know about these circuits is that they have no memory. The output you get depends only on the inputs you give it at that very second. It's all about the right now. So you can picture it like a logical maze. You put your ones and zeros in at one end, they race through this complex network of gates, and bam, out the other side comes a very specific, calculated result.
And you know, engineers don't just throw these things together. It's a very clear-cut process. First, they figure out exactly what they want the circuit to do. Then, they map out every possibility in a truth table. After that, they use Boolean algebra to find the simplest way to get it done. And finally, they draw the actual diagram. It's a really neat journey from a simple idea to a physical circuit.
So, you might be wondering, why bother with all that simplification? Why is it so important? Well, it turns out that step is maybe the most crucial part of the entire design.
And here's why. Every single one of those logic gates costs money. It takes up physical space on the chip, it uses a tiny bit of power. So the fewer gates you can use to do the same job, the cheaper the chip is to make, the smaller it can be, and the more power efficient it is. It's a huge deal. You could almost call it the ultimate engineering jugaad, finding that clever, resourceful way to get the job done with the fewest possible parts. And honestly, this constant push for simplification, it's the reason a smartphone with the power of a 90s supercomputer is affordable for so many of us in India today.
But then, engineers took this idea of efficiency even further. They came up with this absolutely brilliant concept, universal gates. Meet the NAND gate, which is just an AND gate followed by a NOT, and the NOR gate, an OR followed by a NOT. Now here's the amazing part. You can build any logic circuit you want using only NAND gates, or only NOR gates. It's incredible.
I mean, think about what that means for manufacturing. It's a total game changer. Suddenly, your factory only needs to make one type of tiny component. It makes designing circuits way simpler, it cuts costs like you wouldn't believe, and it can even make the final product more reliable. It's a win-win-win.
And this all brings us right back to the phone in your hand. Every single time you make a UPI payment or stream a song or just send a WhatsApp message, what's really going on under the hood? It's millions or even billions of these tiny, simple gates, all flipping on and off, performing this beautiful, logical dance together.
When you step back, it's just amazing, isn't it? Our entire digital world, all of it, is built on a simple yes or no, a 1 or a 0. Which leaves us with a really fascinating thought for the future. What kind of problems will we solve? What new things will we build when we finally teach our machines to say, maybe?